like that. You got it? Will that attract or repel? Attract? That's what you think. Because you know, negative, positive attract, right? Well, not always. Let me show you this. Let me show you how it works. Pay attention, and then after that, you get it in your head, you write it in your little sheet, and that's it, right? So, let's say that this creates a field here. In what direction will be the field created by this here? Up. Right? If this is the current, which is the same as the charge, what would be the direction of the force exerted by this on this? What's the direction of the force exerted by this field, which is created by this, on this wire? Right hand rule again. Fingers along the first vector, which is the velocity, isn't it? And you curve towards the second. So what would be the direction of the force? What the heck is that?
This one, bueno, yo lo hice al revés. I said this is current.
Is this clear to everybody? The force is B cross B. Make sense? Always. The particles are moving into the board.
How is the right hand rule?
Yeah, the right hand rule.
Yeah, but
First vector cross second vector. What you have to have clear is what is the first vector and what is the second vector. The first vector is the velocity. The second vector is the field. Right? Velocity, field.
In this case, the x is velocity.
Yes, that's the movement of the particles. The positive charges. That's the direction of the current. So let's say I'm going to write something on my cheat sheet for the exam. Is the current going the same direction on two wires? They will attract. If they go in opposite direction, they will repel. Is this clear to everybody? You want me to repeat it? You have two wires. Say I have these two wires. And this is the current. If the current go in the same direction, what would they do? Attract. You see what I mean? If the current is in opposite direction, they are repelled. Which is counterintuitive. You people tend to say that like opposite attract equal repel. Well, in the case of the magnetic force, it's the opposite of that. Make sense? So we calculated the force on the wire. If I give you the length of the wire, just multiply by the length and you get the force. Is that clear? So this formula might be tested on the exam, maybe not, because notice that I also give you another version of it. On this side, at a distance 2a, I put what? A negative charge. Remember the first question on the exam? So I have a negative charge going into the board, right? What's the direction of the field at that point? What's the direction of the field at that point? Up. How do you know that? The first question. Right? So at this point, I have a field going up. The size of that field is what?
3.
Mu naught I over, what was it?
No.
4 pi a, remember? We calculated that before. The field is up. You have a charge that is going into the board, but the charge is negative. Is that clear to everybody? So keep in mind that the magnetic force is QV cross B. Got my idea? So the magnitude of the magnetic force is Q, that's the value I give you for the charge, it's a capital Q, right? I also give you the speed, you notice? And this you calculated before. Mu naught I divided by 4 pi a. That is the amount of force exerted by the coaxial wire on that charge. Is that simple enough? What would be the direction of that force?
Towards the center of the line.
Is it? How do you get that? Okay, good, but look at the charge.
Negative, no.
There you go. Let's do it again. I think I have to do this 3,000 times so people get it. The charge goes into the ball, right? That's what I drew.
Next.
Define magnetic force exerted on the particle of charge negative Q, passing at a distance 2a to the left of the arrangement and moving into the base with the speed v. See figure shown above, state the direction of the force. What was that? So once again, fingers along the first vector, fingers along the first vector, you curl over the second vector, and your finger will take you to the left. I mean, to the right, is that clear?
Yeah,
But what happens?
it's negative.
The charge is negative. So just flip it. So if the charge is positive, leave it like it is. If the charge is negative, flip it. Is that clear? In the case of the current, attraction, if it's the same direction, repulsion is the opposite direction. Simple as that. Questions about this? So something like this will be question number 2 in the exam. Is that clear to everybody? And if the exam is going to be on Tuesday, you have plenty of time to study this. But if you practice, solve the problem, and don't understand what's going on, go to the beach from now to Sunday. I want to waste my time, I'd rather waste it fishing, right? En la mar, the
La vida es más sabrosa.
Questions about this? Questions about this? So are you clear on question number 2 of the exam?
Kinda.
Christy, stop like stressing out. The exam is like 5 days from now. This you will get it, because you start paying attention to this, it's a pretty easy thing. You know what I mean?
Divisiones en tercero.
Eh?
Divisiones en tercero.
Yeah, pues,
La tercera pregunta.
That's the easy one. All right, guys. So enough of me solving problems. I solved the second problem, the recitation. If you practice this before Monday, when I do the recitation, you will have an idea of everything I do, and then you know what I mean. You will be great for the exam. Seriously. Question number 3. Question number 3. I'm going to start teaching that content now.
Claro, sí podía entender.
But it's pretty easy, seriously. You will see what I'm talking about. And the reason is because we already went through RC circuit. So I'm going to teach the concept of self-inductance later on. And at the moment, I'm going to speak something extremely important, which is electromagnetic induction. You see what I'm talking about? I'm gonna leave the demos and everything else for after the exam. Demos about how a motor works and so on and so forth. Is that clear, everybody? The torque and all those things for after the exam. Because that's the fun part. Electromagnetic induction. There was this guy called Michael Faraday. I always like to speak about this guy. This guy is, we physicists believe, is the best experimental physicist that have ever existed. You see what I mean? Yes, Tesla. Michael Faraday. Okay, I'm a physicist. Are you a physicist? So, Tesla was not even a physicist. He was an engineer. Thank you. So anyway, these Michael Faraday guys actually went through school. And he was one of those kids, like me, for example, looking through the window all the time. The teacher teaching here, looking through the window, everybody that moves around. They would label that person these days with some signs like ADHD or AD something. They would put something in it, and then psychologists would make our money like it. And they give him Adderall, and they give all this like medicine and so on and forth, you know what I mean? But at that time, the teacher just spit him out. And the mother says, oh, you don't go to school anymore. Come to the house, stop working. Okay? So, great move by the mother. He actually liked handsome things, you know what I mean? And he went to observe one guy, that was doing like demos, you know, when science was like cool in the past? Okay, a chemist doing demos in London, and he was always there like, taking notes and looking at it and being excited about it. Then the chemist had an accident, so he started working for the chemist. You see what I mean? And eventually started doing all the demos of the chemist. And then the chemist like kind of retired and he took over the chemist. You see what I mean? And then he became so this is the guy that we actually thank for the existence of field. You see what I mean? He came to the conclusion that you can have a current changing here and create an effect on the other side. So how these two things are connected. Newton was never able to speak that. In fact, when Newton came out with the law of universal gravitation, that you have a planet here and another planet here and how they attract each other. You know, what happens if this planet disappears? Will that interaction disappear instantaneously? So Newton was actually, he said like he couldn't explain this. If Newton had the idea of field, probably the world would be ended by now because the nuclear bomb would be 300 years before that. So Newton called this like God extension. You know, in typical like Anglican persons, like let's blame God for everything else. So so that's what Newton said. But this guy came out with the idea of field. Is that clear? But he did an experiment which is like great. I can't do it here with but I did it already pretty much. You did the experiment of the magnetic field through a coil, right? You guys do it too. Are you taking the lab for FIU or something? What are you guys taking the lab? But you did probably a lab in which you have a current and you have a field. Yeah. So you saw that in here, right? But this is what he did. He said like, if you have a current going through a closed loop, you see it? Let me give you a loop. Please. I'm not going to do them. A current going through a closed loop. Let's say it's a current. What would that current create? A magnetic field. How is the magnetic field created by the current? How? Well, keep in mind that you're going to have, for example, you grab the loop, right? What are you going to have? Outside, you're going to have a field going out of the board. You got it? And inside into the board, right? So you're going to have this outside, and inside, you're going to have this. You got my point? Is that clear to everybody? So, if that current changes, that field changes. Simple enough? Now, this is actually what he did. And he discovered this by mistake, by the way. Imagine you have a loop, and you're just going to do a circular loop. Most of the experiment in physics is just pure luck. So imagine you have a wire, just a wire. Is that clear to everybody? I'm going to put this wire like this. And let's say you have a magnetic field. I'm going to show you this, otherwise. This thing I have in here is called a galvanometer. All right, it's just an ammeter. It shows current. Is that clear to everybody? It measures current. Let me set it straight because I can't cook it. guess it's broken. This is a wire that is being turned around 800 times. So instead of having one loop, how many loops I have? 800. Okay, what I'm going to do is actually connect this loop to an ammeter. You see the point? So obviously there's nothing, right? So it's like a closed loop. And the ammeter is gonna tell me if there is current going through this. I have this magnet. And look, I'm gonna put the magnet at a certain distance. Do you see the current? Do you see the current? No, you don't. So this loop has a cross section, right? Is that cross section being crossed by a magnetic field? No?
I'm not seeing anything.
Oh, you're not gonna see it, but there is a magnetic field that goes from here there, right? So yeah, the cross section of the loop is being crossed by the magnetic field. True or false? So field times area is what? What type of thing you're talking about there? Magnetic flux. Is that clear to everybody? Because the field is crossing the area of the loop. And this thing decided not to work on me. No, it's like this thing fell and broke. I used to have more. You have to steal more from like.
We gotta go from the center.
Hay que robar más. O bueno, pedir prestado que devolver.
Yeah, you're gonna have to go to Wilson again.
Hay que pedir este prestado uno.
No, I have arrested there. I can't steal from Google anymore.
Just right from Wilson.
Careful, careful, you know.
Profesor.
What happened?
Eso es mío.
No, that's digital, man.
Eso parece un problema cuando el profesor era joven. Bueno,
I have an ammeter here. You see that? And I'm gonna connect to my interface. Right? And I'm gonna connect the end of the ammeter to the loop. It's the same thing I have there. Right? I'm gonna open Logo Pro. Where is Logo Pro? Here you go. And I have current versus what?
Versus magnetic field.
Versus magnetic field. Is that clear to everybody? You can read this number here. Okay. So, when I tell you, you click collect. Pay attention to this guy. This red thing means there is a north pole, right? So there is a magnetic field going that way. Is that clear to everybody? I'm gonna put the magnetic field. Click collect. Stop it. Do you see anything?
No.
Is there is a magnetic flux? Yes or no?
Yes.
There is a magnetic flux. Is it changing? Magnetic flux is field times area. Flux is field times area. Electric flux was electric field times area, right? What it is magnetic flux? Magnetic field times area. So flux is the same concept, no change. Now, see what I'm going to do. I'm going to collect. I'm going to move the magnet away. Stop it. Do you see anything? No, right? There you go. Do you see that spike? That's when I move it away. Let's do it again. You notice? I'm gonna move the magnet towards it. Go. You notice? Then move a magnet away. Go ahead, click. Okay, don't stop. Click. Close it.
When you say close, I know you know like,
No, close means
you know,
stop.
I'm like.
Alright, here we go. Don't do anything. Look, and wait, close it. You see it? What is this? Tell me.
He's telling you that it's spiking?
What is that thing you're reading there? An
An
electric current.
The current
An
is.
electric.
The-
An electric.
The current.
An electric current. Is that clear to everybody? So there is an induced current in this loop. Is this clear to everybody? By just like, go ahead with it. Don't stop it. Look, you see that? Look. You got it? So, what is this guy discovered? That if you have a magnetic flux going through a closed loop, and that magnetic flux changes, right? Then what you will have induced in that loop? A current. But obviously, how can you get a current? What do you need to have a current?
You need a flow of electrons.
That is a current. What do you need to get a flow of electrons?
Oh, differential potential.
An EMF. You remember that? You will not be able to have a current unless there is an EMF. So what's going on here is the following. You saw it, right, guys? It's hard for me to like just tell you. It's kind of like, you know. What happened? So this is what Michael Faraday discovered. One of the biggest discoveries ever, because this is how we produce electricity for the most part. You know what I mean? Electricity is a great way of transferring energy. You got my point there? You have to get it. So how do we produce it here? You get a turbine, and instead of what's my? Instead of like doing this, what do you do?
Go around.
Turn. We do this. You got my point, right? So essentially, you got a magnet, you have another magnet inside, you have something, you provide the mechanical energy to spin this.
Who's going to lead it, man?
You got my point, then, yeah, but you wanna fix the magnet and turn the coil. Because in that way, the design is better. Because you only the magnet.
It's harder than turning the coil.
No, or you mean spin the magnet out?
On its horizontal,
Like this?
like just upwards, it's like spinning.
Instead of spinning.
By the way, today we have these things called like brushless motors. Right, which is the opposite of this, by the way. But yeah, that's what we do, just spin the magnet, as opposed to. But that is like, you know, it's very difficult to use that high technology, very delicate thing to produce electricity in mass. So what do? You have this like big coils, huge coils, big magnets, and then you use like heat or whatever to spin the magnet.
So it's just lighter, like the coil is light, so it's.
Exactly. So, it's good?
That's a motor.
No, that's a generator. This is a generator. You got my point there? You know how do you increase the amount?
Increase the coil.
Give me, you see where you say coil set? Bring the box over here.
Well, you were back in Cuba and you had no electricity.
I'm making one back. Give me that.
Didn't you use it, you know? We used to in my house.
Oh, we have it here. If we sell in the United States, because when there's hurricane, I don't care where you are, it can be in Cuba, it can be wherever you are, no electricity. So one way of producing it is like having a, you know, so for example, you use that to charge batteries and stuff like that, you know, small applications, small time, hopefully you don't have to use that all your life. But it's not in Cuba, it's like anywhere there's no.
That was in Cuba, you know, the light
So-
goes off every single second.
Yeah, so look, I have 800 turn, right? Stay there, you look like good. So turn it. You move. So look at this. Right? Stop it.
Yeah.
Store it. Go to experiment. Click store later on. Now I'm gonna change this for a 1600. So that's the design of the generator. Now what happened with that? Well, the coil is heavier. You got my point? Oh, how can you reduce that? By making the wire thinner. But what happens when the wires are thinner? The resistance is higher. So the current is gonna be lower. So you see all this engineering, this is being an engineer, all these little things together. You got my point there? So you have to take all these little things because one of the most important about engineering is that you have to design so you can sell it. Or it can be used by, you know, you got my point, right? So this is why the economics engineering is so important. You take that class and you transfer it. That's one of the first classes you take. So,
But that's actually very easy on this thing.
go ahead.
Okay. Very easy.
So I'm going to do it. Oh, what's that? What?
No, I just.
Okay, collect again. You got it? No, it's because I turn it, if I turn it like this, go ahead and do it again. You see, what did I change now? The direction of the area. I didn't change the direction of the field, I changed the direction of the area. You got my point, right? So the current came out to be opposite, but when I flip it to the right location, it gives me the same direction. Now, give me one of those cords, how you have the cord. Yeah. So this is an iron core. That's another application that you do. Let me see the effect of putting an iron core in this. Okay. What's the matter? Okay, so collect. Collect. That's why you put an iron core inside the thing, because the iron core magnifies the strength of the field. So all this is designed. So this is the way we generate electricity today. What we do is we have a magnet here, we have another magnet here, and we turn this thing. In your car, it's called how do you call it in your car? Alternator. So two magnets, and then you spin it. Is that clear, everybody? Yeah? What was that? The alternator? What?
Not like inside.
Oh, yeah, I want to show you the alternator. So you understand this, right? This was discovered by Michael Faraday, and it is electromagnetic induction. I have actually one here that you can look at. You know? So what do you do is you spin the magnets inside. You know? That's either alternator or motor. The opposite would be a motor. So pass it around, so you see the magnets and the core inside of them. But this is engineering. I'm just showing you the basics of all this. So you understand how these things work. You got it? The magnets are, yeah, on both sides. But then you have the coils and you spin the coils. You see what I mean?
Oh, I see.
And usually the alternators, how they break.
The wire.
No. It's very uncommon to find the wire burn or anything like that. Extremely uncommon. The way they break for the most part is that the brushes, you know, the metals that connect to the edge of the alternator actually burn. That costs like cents. And you go there and buy an over for $250. They fix it for like 250 millicents. They paint it back, they put them in the same box that you took it, and they give it back to you. That's the reason why they give you $20 for the core.
Yeah.
You know what I mean? But it's usually the brush. You know what I mean? Obviously, we live in America in this like really fast life that you cannot like fix anything. So it's you don't have to go to work tomorrow, but you spend $250, which is like 5 days of work that you can spend like fixing that thing, replacing the brushes. But you know, this is the way the system works. It's beautiful. Anyway, any questions about it? I do the same, by the way, but I have like, what I try to do is I keep the alternators when they break, and I wanna fix it one day, and I keep on accumulating them. I have most of them, I'm gonna bring it here for people when they're not there. What's the markers?
Just sell.
Well, I think we have to know what
Just
you're
sell it
doing.
for $250.
No, I will have to fix it, and nobody's gonna buy it to fix it, nobody trusts anybody these days, especially with Amazon.
Wait,
Yeah, capitalism has changed so much. because the inventive of people has going down. So